Hello, in this video here we shall look at Suvat equations and how they relate to a falling object. And we'll also spend a little bit of time looking at the conservation of energy applied to a similar problem. So, here we have an object, let's say this is a tall building, an object here about to fall due to gravity. Okay, and we're going to indicate gravity as acceleration acting down. Now, let's say we know certain facts. Let's say, for instance, that we know what the displacement, or if you like, the height. But we use displacement. That's a Suvat equation, and we're going to make in this question. We're going to decide. I want to find out the final velocity. The final velocity, and what I mean by that is the final velocity v just before it hits the ground. Often a student will say, well, look at the final velocity 0, it hits the ground, but we're really saying it just before it hits the ground. So therefore everything positive is down, so we're going to have displacement positive acting down, gravity positive acting down. So what will be the final velocity just before it hits the ground? So now, what do we know? We know, I'm going to say what we know, and we're going to use this algebraically. We will know where S is equal to S, so we know the displacement. We know the initial velocity is equal to 0, it's falling from rest. The final velocity is what we are trying to find out. The acceleration, I'll keep this algebraically, acceleration is equal to g, and the time, well, we don't know what the time is. Okay, but we do have 1, 2, 3, 4, and 1 unknown, so this is fantastic. I'm saying that we know S, I'm saying that we know A, I'm saying we know U. So therefore, the equation we'll use is V squared equals U squared plus 2AS. U is 0, so V squared equals 2AS. Take square roots both sides, we ignore the negative result, so therefore the final velocity is equal to the negative root. Of course, you've got two answers to a square root, positive or negative, so the final velocity is the square root of 2AS. And if we said, okay, well, let's say that the height, the displacement over was 10 meters. Acceleration due to gravity is 9.81 meters per second minus 2. We can plug those numbers in there and we get the final velocity. Okay, we'll now look at the same question involving the conservation of energy and see what we get there. So, exactly the same problem, but this time we think about it the conservation of energy. Now, the conservation of energy is conserved. So what we're going to find is we're going to use that the loss in gravitational potential energy is equal to the gain in kinetic energy. And GPE is mgh, and kinetic energy is half mv squared. So, what do we get? Now, this time we're going to call it, instead of S, we're going to say that is a height h. And again, we've got gravity g, positive acting down, final velocity just before it hits the ground b. So, loss in GPE. So, GPE, the loss, it loses h, so that will be m of height h, so the loss is equal to mgh is equal to gain in kinetic energy. Well, it started off with a naught there, it gained all there, so let's say it's got a mass of m, okay, a half mv squared. Potential energy is all being converted to kinetic energy. Now we can cancel out the m's, multiply across by 2 to give us 2gh equals v squared. V, therefore, take the square root both sides and make what we're looking after on the left-hand side. So v is equal to the square root of 2gh. Of course, now, that's exactly the same, apart from replace h's height with s displacement, exactly the same as what we got earlier using Suvat, the square root of 2as, where gravity is equal to a. So you should see that they give the same result. Okay. Now, another thing we might want to calculate from a falling object is how long does it take to fall. So, you're dropping an object, how long did it take to reach the ground? Now, the reason we're talking that now, because that's very useful for when we look at projectile motion. So, same situation. Right, this time, we'll use, say we know that so we've got displacement S, starts from rest, so I'll write down Suvat, S-U-V-A-T. I'll put some numbers in this time. Okay, let's say distance equals 10 meters, we're assuming no air resistance. Initial velocity starts from rest 0. Final velocity, not interested in it. Acceleration is gravity, and I'm going to call it this time, I'll call it 10 meters second minus 2. So here's G equals 10 meters second minus 2. I'm making it simple rather than using 9.81. Time is what we want to find out. So we have T, A, U, and S. We use S equals UT plus a half AT squared. Okay. Now, U is equal to 0. If it wasn't equal to 0, I wouldn't use this equation because we'd have a quadratic, but a difficult quadratic to solve. As opposed to this, which is a half AT squared. There is a quadratic function in there, but there's no other term. So S equals half AT squared. We want to find T, so therefore T squared equals 2S over A, which implies that T is equal to the square root of 2S over A. And to find out what the time is, we plug in 10 into there, and we plug in 10 into there. And then we'd get an answer for how long it took to drop. And we'd be using this as the equation.